So aren't we risking being unprofessional by doing इधर आ ऐसे बीच में निकल जाएंगे अनप्रोफेशनल तो नहीं
ना ना जा
है आधे टाइम अंदर बाहर ही कर रहा है चल नहीं एचपी
Everyone please be seated. We are starting. Please be seated, don't roam around. So, we are going to start. Please maintain silence while they are presenting. Now, the presentation is of Antarang Verma and Mishti Ashutosh Avasthi of Deshbandhu College. And the next presentation of Mehak Rani from Miranda House. Please be ready with the presentation.
Good afternoon. I'm Antarang. We'll be presenting on the puzzle that is time arrow. Time is not a constant, it is not a fundamental. You should know that. We derive time from thermodynamics generally, but we look at a lot today. I thought I would just do Boltzmann, but this is a lot. Anyways, what is time? There's a general definition that time is simply the asymmetry between past and future. Rest you cannot describe because every law is reversible. You put negative time and it will go back to its original state. So for you to describe what time it is, then you have to tell that one is past and one is future. Then there's no definition of time. Here we use a paper from Bernard Chauvenet and Joel L. Lebowitz. Chauvenet proposed 2 points of view, Joel also did, but the realistic point of view is that time is fundamental. Like I said, I don't believe in that. It's a personal thing. That it is independent of anything, and to support that, we'll be using large point car systems that are non-integrable. They won't integrate and they'll lead to non-complex eigenvalues. Eigenvalues are simply just matrices that are complex numbers. That would just mean that they are irreversible. You cannot put negative time and they'll go back. That's simply what that means. And the positive point of view is that there is a statistical definition of time, that it is thermodynamical in nature, and time is derived from the loss of information. That's what Bailian proposed, and we'll be relying on Bailian a lot because Bernard Chauvenet did, and we're doing a literature reading of some sort. Here. The infamous Boltzmann-H theorem. This was the beginning of time. This is ancient. This is how time started. Before this, it was only philosophical debates. This is the first time science delved into physics. Simply that entropy will increase with time, and with increase of entropy, time will flow with it. That was what he proposed and what many believe. But he himself derived it from Hamiltonian, and in Hamiltonian dynamics, it is reversible. So how would we lead to this irreversibility if it is reversible in nature and Hamiltonian dynamics itself? It was from the molecular chaos hypothesis that before collisions, particles have no correlation, and after some time of collision, particles have no correlation. When they collide, they absolutely change velocities depending on the elasticity and everything. He said that because you cannot observe anything before it and after it, it does not exist. To counter this, because it is a pretty simple statement, Boltzmann and Zermelo proposed some paradoxes that if you were to reverse the velocities in a system, it would lead to a state that was the initial state. Because if you go forward then backward, if you were an observer, you were looking here, then look back, you would stay in the same place. How would have time went forward? And Zermelo proposed a more mathematical interpretation using Pointer's reoccurrence. Pointer's reoccurrence is simply that if a particle in some isolated system and we reverse its momentum, that the minus is here, it would be a subset. This is just maths for bringing the subset. The minus of momentum would be the same in the subset of the initial state. He said that given enough time, any isolated system would revert back to its original state. It is a really long time, but it's good, and that would lead to many paradoxes. Boltzmann would have argued that just look at the statistics, but we can look at some more models, some more theory to support Boltzmann. The Ehrenfest-Ernst model. You take one urn, then put 100 balls in it, then take out one ball from that, then put it in the second urn. If you were to do that again, you could either take it out from U1 or take it out from U1 to U2, from to U1, this to U2 to U1, then back from U1 to U2, and you could create many more possible combinations. And for 100 balls to be in this urn, it would take approximately 2,930 billion into the supposed age of the universe. That's a really long time. Now, this is where the maths part starts to come in. I'll try my best. So, look, we're delving into entropy. So, let us take out the entropies in classical mechanics and quantum mechanics. For this, we'll simply use a probability space. For a dp, a small probability space, it would be the same for any t0 or t1. And there's a thing called Liouville's theorem that phase space volume is the same depending on a unitary evolution. Unitary just means that possibilities are the same throughout the evolution. Possibilities remain conserved, and if we derive from it the constant gives entropy, we get a constant. Sorry. And that simply means that any state in classical mechanics is isentropic, that both the states of entropy are same. This is and then we move on to quantum mechanics. This is a density operator. This is a probability eigenvalue. This just means probability for this UK. UK is a state, is a constant state. It's just a quantum state, normal state. And for that, what is the probability? And then this is the density operator on it. Now we'll be using von Neumann's entropy. Von Neumann entropy is entropy defined in terms of loss of information, and we go into the loss of information here. But just know that as you lose information, you gain entropy. This was derived from Shannon's entropy, and Shannon's entropy was just simply that if you lose information, you gain entropy. This is simply mathematics, and we get that it is still isentropic. The thermal time hypothesis. It was proposed by Cohen, Rovelli, Martinelli. They used Tomita-Takesaki theorem, which was a quantum physics theorem. They introduced new dimensions and took it to a Minkowski space. Minkowski space means they took it from quantum physics to general relativity. And using that in quantum physics, this is a flow. This signifies flows of time, and they used a lot of mathematics. I have not shown it here. And pretty much time is a derivative. They proposed that time is a derivation of temperature.
Okay, so in standard quantum mechanics, a system's evolution is time symmetric, and unitary evolution takes place according to Schrodinger's equations. So here this is the experiment. This is the Meera experiment. We found this experiment as it demonstrates the quantum superposition and measurements on the basis of the particle's spin behavior. And according to this experiment, with the spin when passed through this device, results splits into either of the two possibilities, either the going up state or the going down state. So we passed a beam of silver atoms through this device. Silver atoms, because they are neutral, and the magnetic moment of silver atoms is 0, like 4d10 5s1, so the L equals 0. And what we found was that we passed this beam in a right horizontal state, that is the superposition of the going up and going down state. And what we found was that the outcome would always be in the going up state or the going down state. Now this would contradict the information conservation principle of quantum mechanics, where once the superposition is lost, the particle is unable to return to its original state. And after this, we come to the question that if the laws of the quantum mechanics are time reversible, why was this measurement irreversible in nature? So as Valiant stated, that quantum evolution still follows the unitary evolution, and that information is not destroyed. What we have observed is just a part of the system, and therefore the information seems to be lost but is not lost. And so this entire process is called decoherence, where from a superpositionary state it collapses and refers to a single definite state, and that is what decoherence is. One of the examples, decoherence in realistic scenarios can be observed as one of the famous examples of the Schrodinger's cat experiment. When particles at the quantum level interact with the environment around them, the superpositionary state changes to a definite single particle state. And if in terms of this experiment, when the cat is in the box, it is interacting with the thermal vibrations and the air molecules in the box, and these interactions would then lead to the cat being in either the dead state or the alive state, but never the both. And this is why at the macroscopic level we could never see quantum superposition, and why at macroscopic levels processes seem irreversible. We'll just skip the fluctuation theorem. Fluctuation theorem basically describes the probability of fluctuations that would lead to the entropy decrease at quantum level, and it also shows the probability of finding entropy reducing trajectories, which is rare but can still be found at the small systems at short time scales. The quantum fluctuation theorem also addresses the Loschmidt's objections and says that that time is reversible at the microscopic level, but at the macroscopic level, the second law of thermodynamics of entropy increasing is still very much valid. And yeah, that was the end of our research where we just had a bit to the reading of everything.
There is no conclusion for time. Still,
It's
there's
an ongoing
quantum black
conflict
hole
whether
theory.
time is fundamental or emergent, and that is what we studied over.
So it's simply mathematically show that Newton's laws and quantum equation are always
Newton's laws or Schrodinger's laws are time reversible. I have not done that, but in every research paper it was written that they are time reversible.
Newton's, if you apply Newton's laws, the Newton's equations, so if you reverse the velocities, if you reverse the parameters, it would still work the same. Or you would just get the time in negative, and then you would get time in positive. They work the same. You get the same value. And Maxwell's electromagnetism equations and even the general relativity also for the same principle that they are time reversible. Quantum measurement is one of the newer concepts which states that there can be time irreversible fluctuations found at in the laws that are considered to be reversible.
And suppose when we're talking about statistical definition of time, when a system reaches equilibrium, there is no favorite direction of time. How do you tell in that situation that which is the error?
So, so one of the assumptions that it's taken, entropy is either constant or keeps on increasing. So in quantum mechanics, state of equilibrium would be where we have the knowledge, where the superpositionary state would be the state of equilibrium, and as the processes take place, and we come to know that okay, it went from superpositionary state to a single definite particle state. There's a lack of information. It changed from something to something and can't return back to something. So we related it to entropy, and that's how it is.
And what is lack of information?
That we don't know.
We cannot observe every
We
particle.
cannot observe. If you take
Like if you were to have a lot of particles and they started to collide, even 100 particles.
What do you mean by information? If you have particles, what does it mean?
okay,
And
so
that is defined in physics by mathematics of the space you will take. In general, that is the space you will take in box space. But in general terms, that after some time we cannot measure all the interactions of a system. That is simply it. But
Somebody you mentioned probability eigenvalues. What is the meaning of probability eigenvalues?
the probability of that quantum state, quantum isolated system being in that quantum state. That's what I understood from it. I have not delved into it that much. I'm a first year, but I have explanations for all of these equations of my own, but it will take a lot of time.
You mentioned eigenvalues could be having, so you understand from eigenvalues. What exactly do they represent?
Eigenvalues from what we did, they were mostly used for probabilities, to define probabilities, and there are linear
Eigenvalues were used to define probabilities.
probability of an eigenstate.
Probability of an eigenstate.
Yes, that's what. And their row matrices, open up their representation of row matrices. And like I can go over, but it's okay. And like this is how quantum evolution takes place. This is von Neumann's entropy. This is how you would write a unitary equation. And I have also done the derivation. I've seen, tried to understand, but this is not something that can be done in a 12 minutes presentation. It's
All
like
that.
we info dump pretty much.
Thank you.
Thank you, Ashutosh Sharma and Nishki and After speech, does anyone have a question?
Yes.
Like, I just wanted just one.
Yeah.
My question is, can you just make a clear picture about your presentation?
Yes, it's a pull back and push back between the positive and realist view. We cannot draw conclusions.
Are you looking at the paradox of time reversal? Is that what you are trying to? Is that what you want to talk about?
My main motive from this is that to proceed because we haven't done that properly, but how in quantum physics and how in normal physical laws we use time.
Quantum mechanics is very much longer, but you usually say classical and
Classical, yes. And in general relativity, we start using conical times and Lorentz diamonds. How do we translate from this to that? That was my question furthermore. So I tried to put in all the information I could find to relate both of those, but it has never been done. It is still an ongoing process. And this is pretty much like we just did research and presented what we researched on. This is Bernard Chauvinier's paper on arrow of time. If you would go through it, most of it would match, but we delve into the references, then back into the references. That's why it's all over the place, because no one has yet to define a simple arrow of time.
Okay, I have a just very small thought experiment. So you made a statement that entropy of the universe is continuously increasing.
That's Boltzmann.
Okay, let's say Boltzmann made that statement. So now consider that we are sitting here and the entropy of the universe is increasing. Every time it's increasing. Let's say we get this power to stay here in this form and entropy keep increasing forever and it gets saturated. So what will change for us? Let's say entropy you have reached in a state of complete chaos, no complete randomness. What will change for us sitting here?
At that time, at complete chaos, there will be a lot of time reversal, then back to moving forward, because there will be like you were saying that we are stuck at one entropy. Pretty much you are time traveling in my perspective by Boltzmann definition, that you are stuck in the past and you are seeing the future.
Fine. I was asking about, are you familiar with something called thermal death of the universe?
Yes. Thermal, there's lots of thermal cooling expansion. I delved into that, but not that proficient. And it would be such a molecular chaos that there could be a possibility that all the particles are moving in this direction, then back in this direction. Because you're an observer outside that system, you could tell that it is future or past. But if you were in that system, there would be no meaning of past or future.
Thank you, Antaram Gurma and Mr. Ashutosh Awasthi. Now we will be presenting Mehek Rani, and after that I would request Robin Seth, Uni Anand and Reza Fareem to be ready with their presentation.
So basically, first of all, I am Mehek Rani from Murata House, University of Delhi, and this is my research which I did in my second year in an internship under DS Kothari Center of Research and Innovations. And my basically topic resembles with material sciences, and I have made a gas sensors. I'll show you how. So first of all, the title of my paper, this is my paper, and it was published in November in Jamia 6 International Conference. It is in the final process, and soon it will get published, but this is the paper which I submitted there. And the title of my paper is Re-Synthesis of Nickel doped or incorporated tin oxide nanoparticles for improved gas sensing applications. So basically the gas I sensed was SO2, sulfur dioxide, and the material, the kind of nanoparticle layer I used was tin oxide. And I draw a comparison between bare tin oxide and nickel doped tin oxide, that which will give a better response to SO2 gas. So the best selling point of this research is that we have not used any harmful chemicals. It's purely green synthesis. The nickel nanoparticle was extracted using guava leaves, and the tin oxide nanoparticles was extracted using orange peel and tomato peel. And we did a lot of research, but in this paper, the 50% of the research is there. In this, we have just drawn a comparison between their SNO2 and nickel dot SNO2. But we have prepared all these things using orange peel and guava. So, orange peel and tomato peel. So, with that, we concluded that the nanoparticle that extracted using tomato was giving a better result. The yield was too good. And how we prepared all these things, I'll show you. First, the preparation process, we took a thin slice of tomato peel and orange peel, just dry it, and then we mixed it in DD water and then stir it for a time, heat it, so that the reducing agents that are present in the leaf and the peel comes into that particular solvent in which I am dissolving it. Then after that, once the particles were extracted, then I used gold aggregates, which was provided by the college only, and then I use it as a substrate. Then upon this, I made a very thin layer of nanoparticle which I extracted using these three services. After that, the technique I used to synthesize. Oh, so sorry. So yeah, so sorry. And I was there, like the spin coating I used for making that layer of thin film, and we made thin film on like glass also for characterization and all those. I'll show you in the next slide. So we use the spin coater because at that time the time constraint was there. In a 1.5 month we have to complete our the internship period. So the faculty told us to go by this technique. So using spin coating, drop by drop, the nanoparticles we extracted, we put drop by drop on that gold LEDs. Then after that, we get to settle down the layer. It was annealed and calcinated at 400 degrees Celsius for 1 to 2 or 3 hours. And when the layer was formed, when the layer was uniformed, and characterization भी आ गया था from Department of Physics, the characterization for XRD and for FTIR was done from Department of Physics, and UV based we did on our own because that was the machine was available in our college only. So after that we proceeded with the gas sensing part. The gas sensing machine was totally made by our faculty members. They made the whole machine in which we used to keep our sample, which we have prepared in the chemical labs. Then after putting that sample there, we started from 50 degrees Celsius to 160 degrees Celsius. उसको 10 degree gap पे 10 degree के time gap पे हमने gas को release किया उसको chamber के अंदर. That was purely of vacuum, and पूरा an electrometer was connected to that gas sensor machine, and then we measured the resistance. Like my gas sensor was totally based on resistive type gas sensors. Like the resistance was decreasing when we are like putting the SO2 inside the chamber. So the concentration of SO2 was quite less, like very few, like in ppm it was there. And then after, you can see, I'll show you the graphs at the next page. These are characterization. You can see this is for bare SNO2, this is for nickel dot SNO2. The color is not showing, but there are red peaks in this graph, and this is like purely for SNO2. And the red peaks that differently come because of nickel. We can see that the incorporation of the nickel was so good at that particular time when we made the layer. The uniformity was quite like good. Like we saw in the research paper that the yield is less using green synthesis. If you use the chemical, the yield is obviously high. But we are getting that much good result using this green synthesis, then we can make it for hydrogen gas sensor, for SO2 or whatever. Because world is going toward hydrogen fuel. So these sensors at that particular time when we are using the technology using hydrogen fuel, and if hydrogen is getting released, then it's a chaos. It's a big chaos. So to handle such kind of situations, it is a technique that we can use. And you won't believe, in 119 seconds, using this 1.5 months, this research is just of 1.5 months. And the recovery and the response time was of 51 seconds and 119 seconds. It was recovering, it was coming back. And the resistance was of 50 giga-ohm, and it is coming to 4-5 giga-ohms. So using Arduino and so much coding techniques, we can sense, like we can use the buzzers and so many other techniques that we can detect the SO2. And further, we use it for NO2 also to check the sensitivities. Like the tin oxide is the material that can sense humidity also. So to see all these things that it is sensing other gases also or not. But yeah, it is proven that SnO2 material can sense hydrogen oxide more efficiently. But there are a lot of papers, but they are on NO2. So we read so many papers and then we come to a conclusion that let's sense this first. Let's see if it's sensing or not. The process is completely reverse. For NO2, the resistance will get increased, but for SO2, the resistance is getting decreased. So that's why we chose SO2 and we checked, and then we sent it for FTIR, Fourier infrared spectroscopy. जो वाइब्रेशंस की जो ये पूरा वेवलेंथ है, ये सब जो एंगल्स है, वो सब कुछ बहुत ही स्टैंडर्ड डेटा के साथ मैच कर रहा था, एंड वी चेक्ड इट. बट वन लास्ट थिंग, इस पेपर को सबमिट करने से पहले वी कुडंट get the results for SAM and TAM, and because the department was busy, they said it will take 1 month and we have our conference, so we cannot add this. And after that, the result came, and with the parameters which we wanted, like nano material hona chahiye, thin film hona chahiye, that was pretty good. So after that, this was done by me in our college, UWiz, and इसका जो band gap है, tin oxide का होता है, that is 3.6, near about 3.6 electron volt, matching exactly 3.6, and then with nickel incorporation, the band gap decreased to 3.3. They show that after the incorporation of nickel, the sensitivity of the sensor increases to a certain value, so that overall after sensing after so many different temperatures, we concluded that 100 degrees Celsius was the optimum temperature, because the response, recovery, sensitivity was best at 100 degrees Celsius. But at 60 and 70 degrees Celsius, even at room temperature, it was sensing, but the response were quite less. It was taking 1 minute and kind of thing. But yeah, at 100 degrees Celsius, you can see the response and the recovery of the thing is at maximum level. And after that, this whole process was done. And in conclusion, I would like to say, it's just that nickel incorporated tin oxide was better in overall performance. At some temperature, we can see that it is performing better, whereas SnO2 is performing better. But in overall performance, if we consider the all parameters, sensitivity, recovery time, response time, each and everything, then we come to the conclusion that nickel incorporated tin oxide material was a better performer in all the ways. So this was my presentation, and I will love to take questions now.
So when you're talking about the resistance of gas, what kind of relationship does it follow?
The relationship is like it's more about chemical reactions. When the sensor is exposed to air, it's like सबसे पहला reason है कि मैंने nickel ही क्यों drop किया? Why not other things I have done? Comparable size का tin के साथ nickel का size है, tin oxide के जो ions का size है, tin का size है, that was matching, like very comparable. This a very few difference was there. So वो अच्छे से drop होके उसकी sides को replace कर सकता है, first of all. And second, when the sensor is exposed to the air, like the dropping of nickel will create oxygen vacancies. Oxygen vacancies in the sense that oxygen exists in C6, oxygen negative, oxygen 2 negative, oxygen 3 negative. So that oxygen will take out electrons when it is exposed to air. पूरे sensor से electron लेके चला जाएगा, the conductivity decreases. बहुत ज़्यादा मतलब पूरा conductivity decrease हो जाएगा, तो मतलब resistance बहुत बढ़ गया sensor का, जब वो air की contact में है, oxygen की contact में है. When I release SO2, तो वो SO2 क्या करेगा, सारे के सारे electrons उसके पास है, वो sensor को वापस दे देगा, conductivity increases, resistance decreases. So that's the relation I use for that.
Is there any empirical relation or?
There is no relation. It's just more of reactions that we read in chemistry and all. It's about reaction. There is no relationship between them.
And there was one experiment that we've done is extracting single nanoparticles from organisms, and we realized that the yield was very close to poor. Like
Very close to?
Very close to poor. Like we
Poor,
had a lot
yes.
of orange peels and single nanoparticles. So like, I don't know we have
You won't believe.
Are you getting some feasible results from this?
Yes, I show you. In 51 seconds, I am getting the recovery time and response time of the sensor. That's when we published the paper, right? Because we were getting this one. And for 15 days, out of 15, more than 15 days, we had just research paper. Then, when it comes to preparing the sensor, it was a very, very, very hard task, because if it just slipped from your hand, then it's wasted. You have to remake it, and we were using gloves, we are using ethanol again and again, and सारे सब कुछ यूज करा रहे कि जिससे सैनिटाइजेशन पूरी बनी रहे, कोई भी बाहर से पार्टिकल इसके अंदर नहीं आए, तो वो सब ध्यान में रख के अगर हम करते हैं तो ये अच्छी आ सकती है। एंड मटेरियल पे भी डिपेंड करता है कि लाइक अभी वी हैव कंपेयर्ड दैट ऑरेंज मिल्क और टमाटो में से टमाटो ने ज़्यादा परफॉर्म किया, बट यू कैन गेट अ कंक्लूजन एट दैट कि क्या पता रिड्यूसिंग एजेंट्स जो ऑरेंज के अंदर तुम्हारे नए पार्टिकल्स को निकालने के लिए है, क्या पता वो कम use another material. Material was same, but tomato was giving better results in my case. So the yielding is good with the tomato. You can change your material, you can change your extracting kind of things.
You talked about temperature that the results were best at 100 degrees.
Yes.
So how does temperature control the results in this case?
My temperature control result in this case was like there is a
I mean, that's your observation. How would you like to justify that?
How I would like to justify that, I mentioned that I started from 50 degrees Celsius and I go to 160 degrees Celsius. And that machine was having the temperature controller and all of these things. We have to just press and 1 by 1 degree वो increase हो रहा था. There was little bit fluctuation like 100 से 101 हो जाएगा क्योंकि temperature we can't control.
That's okay.
But at 100 degrees Celsius, why I am saying it's my optimum temperature, because response recovery time sensitivity was high at that temperature. Like 51 seconds, which I am talking about, it is at 100 degrees Celsius. Less than 100 degrees Celsius, it's showing pretty not good result. Like not sensitivity is not that much good. Recovery time is high. So that's kind of problem we saw, and we come to a conclusion that 100 degrees Celsius is a good temperature for us. So soon, if we will take more kind of, अगर हम बहुत ही ज़्यादा अच्छे से बहुत ही ज़्यादा उस तरीके से इसको डिज़ाइन करें, लाइक रीयूज स्पिन कोटिंग, एंड यू नो दैट यूजिंग स्पिन कोटिंग यू कांट गेट यूनिफॉर्म लेयर. If you will use evaporation techniques, sputtering, laser beam incorporation of this nickel nanoparticles, I can bet it gives result on 60 degrees Celsius, 50 degrees Celsius. So I think getting at result at 100 degrees Celsius was because of the uniformity of the layer, because there was not that much good using spin coating. So we can use other techniques to make a layer.
But conducting polymers will do much better. They work at very low temperatures as compared to
Yes. That thing I would like to say that the time period was very less. So we followed the research paper done by our faculty members, like Professor Monica Kamal guided me for this, and few other faculty members also. So they suggested us to work on semiconductor.
Also, when you talk of sputtering or you talk of thermal application, they cannot be used
Using this,
all-
yes. On this.
all
I am mentioning that because I will change the material then. I will change the
then you cannot compare your orange tea, I mean your tin oxide
That's why
and nickel oxide.
they said us to go with spin coating because this material was
You
not
cannot
that
use thermal application.
Yes, we can't. Because मैम वहाँ पे जो factor है वो melting point आ रहा है. And when metals का melting point is quite less, then it will not be.
That's why you put conducting polymers in that.
Yes, yes.
Polymers can be used because they can be
Yes.
I have a question. So it's a good work.
Yes.
So then you have shown us this infrared spectrum. So what information does the IR spectroscopy gives you about the molecule?
Okay, so sir, after the results have came from the department, we saw that the vibrations of oxygen bonding with tin and the vibration of nickel bonding with oxygen and tin. So the vibrations, we saw that at what particular wavelength we are getting the vibration, at what particular wavelength we are getting the dip. So we matched with the standard data, and then we concluded that this particular is existing. So this was. And now I came at my college. You took my virus. I remember you. Nice meeting you again.
Thank you, ma'am.
You don't get extra marks for saying that.
Now I would like to invite Robin Singh, Reza Fareem and Bhugi Anand from St. Stephen's College to come and present. After them, I would like to let now Borshan Ghosh to be ready with their presentation.
So, good afternoon, everyone. So, to start with, one day I was absent-mindedly spinning a coin on my desk, watching it swirl, wobble, and do some crazy stuff before coming to rest. I wondered if physics would actually predict this topic. And this question led us to dive deeper into the topic, predicting the motion of a spinning coin. So, as I searched more about it, I found that a scientist named Joseph Bendick actually developed an educational toy called an Euler's disc, whose motion was very similar to a spinning coin. So let's have a look at the demonstration first. So as you can see that this Euler's disc is spinning on a concave glass surface. So there is negligible friction and hence minimum energy losses. So unlike a coin which would stop really early, this would go on for a remarkably longer time. Now moving on to the motion of the actual spinning coin. So this is being spun at an angle. And as you can see that it's being spun on a highly frictional surface, right? Table is a frictional surface and it has some irregularities on the surface as well. So its motion would come to a stop much quickly. But the motions are very similar. You can compare it to Euler's disc. So when we actually saw the spinning coin, some of the phenomena are very obvious. The first one being the precession. Imagine spinning a top. When you view that top from above, it doesn't just fall. Its axis tilts slightly and you can clearly see that tilt tracing smaller circles. Those circles will keep getting wider and wider as the top will lose energy and fall. This phenomenon is called precession. The same thing happens in coin. It also precesses along z-axis. The only difference is that except the top which has a unique point of contact, right? The coin doesn't have a unique point of contact. So if you view it from above tracing those circles, it will be tracing those circles on the below surfaces. Next one is nutation. Nutations is, you can say, that the jerky motions or rapid oscillations which are superimposed on precision. Third one being phase spinning, which is actually a very interesting phenomena, because if I demonstrate it, you will really know that it's nothing new but a combination of processes that we already know. So suppose this is my first contact point. So I treated an angle from the vertical, small angle, and then it, as I mentioned, it precesses, and the new contact point changes to I take a slightly larger angle from the vertical. I repeat the same process, and now this contact point changes to 3. So I am rotating it like this. If you get close attention, I am rotating it like this. But the phase spin, first you saw 1, 2, and then 3. So the phase spin is like this, in this direction. So it clearly proves that they both are opposite. Precision and phase spin are opposite. The fourth one is circular motion. See, all the phenomena which are happening, they are not happening at one place, right? The point is having some translation motion. You can say it is tracing some circular motion for spirals.
Now we have some assumptions in our model. Firstly, the thickness of the point we take is negligible. We are taking the rolling without slipping condition for static friction, and we are ignoring rolling friction and air resistance. Now let's have a look at the coordinate system that we are considering. So one is the fixed frame x, y, and z, and the other one is the rotating frame 1, 2, and 3 that is stuck to the plane of the point. 1 is perpendicular to the plane of the point, 3 is along that, the symmetry axis, and 2 is perpendicular to both. A here is the radius of the point. Some further symbols that we would be using in further calculations are alpha, that is the angle between the plane of the point from the horizontal. Then we have capital omega, that's the precessional frequency around the z-axis. Another important frequency that comes into play is omega 1, along one of that. Now this is not actually the phase spin that's happening. That's composed of two components. One is the phase spin, that is omega relative, and the other one will be a precessional component, that would be capital omega cos alpha. So the total angular velocity of the system can be composed of two parts, omega 1 to 3, that is the angular velocity of the trial with respect to the phase spin, and omega relative, the phase spin, that would be the angular velocity of our coin with respect to the trial. So because we are taking the rolling without slipping condition, we can write the value of VCM as follows. And since there are two forces that are acting on the coin, one is gravity and the other one is F at the point of contact, so we use Newton's second law. Then we write down the change of angular momentum and the torque equation, which will be due to F, since gravity would not produce any torque around the second axis. Now since F is common to both of them, we can eliminate F and write down the final equation. RC. So at first we considered a very simple model that when the coin is falling down, the center of mass will move like this, vertically downwards along the z-axis. But then we realized that that's actually not true for the physical system, because when you spin a coin, it will never happen that you give it zero translation effects. There always will be a non-zero component, and hence the center of mass will also trace circles. So we can write the position of that circle, the center of that circle in such coordinates, and the final value of RCM that we would be using will be this.
Now in the general case, since static friction is present, the coin will translate in circles about a fixed center point. So using the new expression for RCM, we find the second derivative, and like explained in the force analysis part, we go through the same procedure and write the following three differential equations. Now since these are differential equations, we in Python we use backward differentiation formula, which is a differential solver, to solve these equations, and we get some plots for our quantities. Now before I show you the results that we got, I'd first like to show you this plot which we got from a paper from University of Sydney, where they had actually performed this experiment in using laboratory equipments, and they had got this result. You can see that the theta, which is the angle of the coin with the ground, it has a general decreasing trend. However, initially it oscillates, it is oscillating about the general trend, and the oscillations are initially large and they decrease as time passes. Now moving on to our results. These are the initial conditions that we have taken for our results, and these are the results that we got. Now this is the plot for alpha, which was theta in that paper. Now immediately you can spot some similarities between the two plots. You can see that R alpha is also has a general decreasing trend. However, its oscillations about the trend are much more profound. But the oscillations are also, you can see that they are also decreasing with time. However, since air friction is not there, this process will take a larger amount of time. So moving on to capital omega, which is the precessional frequency, it is also oscillating about its general trend, but it has a generally increasing trend. Okay, now why is that? First of all, this is something that is expected from the model, as you saw in the demonstration earlier. As the angle of the coin with the ground decreases, the precession increases. The precession would blow out. Now, if I take specific points, for example, let's say I consider this point, this timestamp, and I consider the same timestamp here. You can see that when alpha goes to small values, the precessional frequency blows up. This is expected. Now moving on to omega 1, you can see that it is also oscillating, but it also has a generally increasing trend. Now for explanation of that, first of all, it is also expected. Here, let's consider the first equation. Now if I take this term on the other side, then the value or the sign of omega 1 dot completely depends on these two quantities. Okay. And based on the plot that I just showed, capital omega is going to be positive plot. So it comes down to alpha dot. And since alpha is oscillating, it is sometimes increasing, sometimes decreasing. So alpha dot will change its sign. As a result, omega 1 dot will also change its sign, and we can see that omega 1 will oscillate, which we can see. But since alpha has a generally decreasing trend, omega 1 will have a generally increasing trend. Now moving on to the total energy of a system. Now what do we expect out of the total energy? Since the only non-conservative forces that we are considering in a system are normal force and friction, static friction at the contact point, they are actually not doing any work. So by theory, the total energy of the system should be constant, which you can see. Like this is the total energy. It may not be clear here, but this is the potential energy, and here you have the two types of kinetic energies, right? But you can see that these, like the bifurcations of the total energy, they are oscillating with time. But there's some total energy is not oscillating at all, which is a good sign. But since it is still slightly bent, it is not completely constant, because obviously this is a numerical integration method. This is an approximation of the actual.
Now what if we change the radius of the coin we are taking? So the first graph is similar to what we just saw. What if I double it? We see that the coin flips to the other side. Now there may be many reasons for it, like the distance between the center of mass and the contact point will increase, torque will increase, there would be a higher precession at the starting. So we see that it flips to the other side. What if I make it 5? Same thing will happen, but we'll see precession is more.
So moving on to some improvements that we can make in our model. The first one is, as you saw that we were doing mathematical modeling. So it's very difficult for solving the differential equation to define the initial conditions and the constants, right? You can only have some rough idea or some intuition about the static angles as well as the other quantities. But if we experimentally perform this experiment, like using a motion analysis tracker and maybe a better solver, you would get much better plots. The second one is obviously, as we all know, that the coin doesn't have a negligible thickness, it has a considerable thickness. And if we take that into calculation as well, it would obviously make some effect on that, because now the forces of friction and the normal would be active on a region and not a single point of contact. Third one is obviously we can take air drag into account. Thank you.
So, from the study, can you also estimate the number of heads or number of tails that will get out of the experiments? If there were?
Actually, it would be like very because like there are multiple processes at play, so it would be very difficult to predict that. But you can like make general assumptions like we showed here. You see, like when the radius is increased of the coin, right? The center of mass will be much more further as compared. Like, this is a smaller radius, this is a larger radius. So the torque will be larger. So you can see that it falls on the other side. So you can make like general statements like that, but for a like particular setting, it would be difficult to say.
Also, this is very unphysical as well, ignoring rolling friction and the air resistance disturbance.
And one more thing you said is when you pick a point from the start or when you surface, is there a specific reason or it could follow any other shape?
No, it would be like if you actually do it, it would be in spirals. Now, like if that is because see you will never be able to give it like a perfect upward force. Okay, so you will always give it some translation of horizontal velocity. But even if we ignore that, like we ignore that in a system, we like assume that we are giving perfect upward force. So even in that case, because of friction and since it is rotating, it would move in a circle.
So is it an equation of circle or is it just an observable number?
Like this is for the RCM. So you will get this, and this would actually be like fixed point. Like the circle's center will not actually change.
That taking a perfect model actually could tell you observable reality, the static friction will provide that sensible force of the face spirals. And that's because it will not remain at the same point because there is a non-zero transmission in the spectrum.
What work have you exactly done there? I mean, these equations are standard, you solve them.
Yes.
You solve them yourself.
No, like we referred to a paper where they had solved them and we had worked through this. We had actually what we had done is like the solving of the differential equations and non-dimensionalization, plotting them, and the analysis of the plots. All of that we have done.
Equations are on paper, but we have developed
Computations, yeah.
solving the differential equation, then analyzing the behaviors.
So those results are already available. Could you verify them, or I mean, there's something new that we've done?
In different papers they consider different models. Like we consider another paper as well. Like how we said here about the thickness of the coin. We consider another paper where they had considered thickness of the coin as well. Where they had taken like a region for the normal force as well as the frictional force. But we thought that was like very complicated to deal with. So different models would give you different results.
We can mostly get equations, but the computation with it that actually matches what happens physically when we split a coin and twice the increase the time, capital omega will increase. So our graphs match.
You must have had just stable memory. If you come here and do this when you they must have had some initial changes.
Just these three equations.
Yeah, the people do not have actually.
And doing this they did not
They didn't solve it.
they didn't have any results.
Yeah,
It was just a theoretical analysis that we were looking at. So, but we can always solve it in certain ways. So, that in the check. You see,
Yes, what you're getting exactly what I'm saying.
if we relax because the problem that we're facing. You could have actually tested it for, let's say, relaxing one of the conditions.
So we did do that.
We did it.
Yeah, we did do that.
So did you try that then? So what happened then? Were you still not getting?
Like sometimes it works, sometimes it does not work.
Sometimes it works, sometimes it doesn't work. Because it was some initial condition.
Yeah, like it is very sensitive
What
to
I'm
the
trying to say is that you choose a certain situation which can be analytically solved. Choose some situation which can be analytically solved.
It's actually very difficult to find the exact values of capital omega and omega. That's all qualitative.
That's what I wanted to know. Did the paper, when was the first graph that you showed, where you said you did some experiment?
We did it using a motion analysis strategy.
They did publish any data.
Okay.
They only give you.
You don't have any experimental data, that's why if you directly want to do that, the actual data will be
I was saying that that would have been a test for the robustness of the solver.
Yeah, actually, like we looked a lot into like getting actual data, but there was none.
That is not possible because there are different frequency parameters and you cannot provide all. But we have done qualitative analysis and we have tried to match.
So what for this? So this is what you.
Yeah.
I thought something else other than.
Are you familiar with this tracker app?
Motion tracker.
Motion tracker app. So have you used it? So you can record a very high quality video and that will work for you. It's very easy to get the experimental data for you. It will very quickly verify your whole analysis. You can work on both
Yes,
sides.
sir.
Thank you.
Thank you, Robin, Bhumi, and Dida for the presentation. Now I would like to invite Borishan Ghosh from Ansraj College for his presentation, and next will be Mansi Dish from Ashoka University. Please be ready.
If we are
Okay, so my name is Bhushan Ghosh. I'm pursuing my third year in Ansraj College. This is a small subset of the work I did in Polish Academy of Sciences regarding solving certain hyperbolic conservation laws numerically and then comparing it with benchmark cases for analytic purposes. And the rest of my presentation is to make this sound less boring. You have a fish tank. There's water in the fish tank. You want to simulate what is the time evolution of this level of water. So you discretize that space. You draw a line. You mark it off x naught, xi, xj, and so on. You mark off the interfaces between these discretization as xj half, and so on. And at the top, you see what the level of water is. You call that u. Then you get rid of the tank, because you realize that if you replace u with anything and you have the equations that talk about the time evolution, you can make statements about anything, because water in this case, there cannot be water coming into the water out of nowhere. So it follows the continuity equation. We know the continuity equation. This is that no matter what, if there's a conserved quantity, it will follow this equation, and it does not matter what use, it does not matter what flux is, as long as this continuity equation is made, you can do incredible things. So this is a partial differential equation. The first thing you do is integrate it. So you integrate it, you find cell averages, like over some discrete xi, and you have xi plus 1, xi minus 1. You have these discrete spaces. You have a line. This is the line. This is the line you want to follow through t is equals to n. You want to follow it through t is equals to n plus 1. Fine. So you have to integrate through time. Then you realize that there is some flux here that you cannot solve because you know this. Yeah, you have discovered the finite volume method because all of the way all engineering applications, if you want to solve this problem, they will use the finite volume method. This would seem like a very simple problem to solve. Let us consider the simplest case. The simplest case is that you have a cube, you have a boundary wall, you have a constant value of quantities u left, and you have a constant value of quantities u right. Simple as it can. You have some set of quantities here, some set of quantities there. You remove the water, you see what happens. What will happen is that there is a large amount of quantity here. It would make sense that it will move here. So you will have a shock wave going here. You will have a rarefaction wave going here, and this is contact discontinuity. You want to simulate this. This is the problem. Now, can this be solved? Sure, we have the quantities at UN, but do we have the fluxes? You don't know the fluxes. You cannot know the fluxes. In fact, no one knows the fluxes. In fact, the rest of my presentation is to find how to do it. How to do it badly. Because this problem, this is called the Riemann problem, can be solved analytically, but for a big enough space, this cannot be done in general. The bigger problem is that this is discrete. You know that integer programming is NP hard, it cannot be done, but convex programming is easy. Same way, you convert any problem from continuous domain to discrete domain, it suddenly becomes unsolvable. So, how do we begin solving? This is Sergei Budanov. He was working in Soviet Russia during a time when solving this problem was extremely important. There were times of we wanted to find out how rockets will work, we want to find out how to optimize hydraulic presses, we want to optimize nuclear power. So, let's see how Budanov. Budanov wants to approximate the big F there. So, what do we have here? We have some quantity ui, some quantity ui plus 1. I want to find how much flux is going from here to here. Let's call it flux I plus half. Similarly, some quantity will come here, but let's say this is going here and this can be negative. Fine. So what we're going to do is find the average value of here. So you have some idea of what the average is here. This is the average value of the two immediate cells. And then you find what is the flux here and what is the flux here. You subtract that and balance as an account, you do all the thing, and then you get some amount of flux, some amount of quantity you expect to be at ui half. The interface quantity. You plug that into the flux, you find how much flux is supposed to be in this surface. This is the first order Budanov method. It was one of the first and the most widely used ways to do this. This is very simple. This works. This is the paper of Galilei Salt. The paper was written in 59. He made a collection of all of the methods that were used during that time, and then he continues to give random sampling Markov way to do this, probabilistic way to do this. During his survey, he adds this graph. My job was to take all the schemes that are given here and convert that into something that can be implemented in Python. Fine. This should seem easy. You have a state, you initialize it, you keep applying the Budanov update at discrete time steps. When I do this, I get this. It looks good, but there are some discontinuity. I ignored this thinking that this is some problem interfaces with data management in Python. Might be some problem with my memory, but fine, this works. We'll move on. This is the Rushanov method. I'll just go through a bunch of other methods. We don't need to focus much on this. This was a very interesting thing. You see that phi there? This phi is an artificial viscosity. This introduces viscosity because what problem was happening here was at like when you have a quantity here, when you have a quantity here, you want to find the derivative here that is shoots to infinity. That is the biggest problem. We want to get rid of, we want to have work with physical quantities. We cannot have infinites popping out of it. Fine. Then let's look at McCormick, how McCormick did it. So this is a very popular framework. You have a predictor framework that takes a large step to the right and then corrects it by taking a half step back. So it both incorporates the forward difference and the backward difference. You might think that this might smoothen the difficulties at the infinity places, but turns out it is something very clear. The tube blows up. You plug that and you test it out with good enough hundreds of times. Good enough works. Absolutely every time it works. You try different implementation of the state. It works. McCormick, tube blows up. Let's see. But this is good enough. This is Swords paper. Somehow this is, but this looks perfect. Why does it look perfect? Let's step through our animation. So you have some amount of quantity here and you have no quantity here. So yeah, it works as is expected. The particles start moving from here to left to right. Information is traveling from left to right. So this velocity goes up. Fine. It is working fine. Let's see the next 20 steps. God, density has shot up to billions. And by the 40th time step, it is that you have to. Why is this happening? How do we fix this? Turns out that McCormick does the forward update. It has accumulated some error, and does the backward update. It does not fix that error. It is not. It does not. It is fundamentally anti-diffusive in nature. So it accumulates twice the error. So if you had plotted Duganov updates, it will be like this. So even at some t equals let's say 100 times it shows you something reasonable. But by that time, McCormick has shot up. So we need to fix that. We introduce artificial viscosity. You have your initial quantity, and you look left, you look to right, and then you look at yourself, and then you realize you have gone too far. So by a damping parameter nu, you go down a little bit. You apply artificial viscosity after the state has been initialized, and then you apply viscosity, you apply the Goodenough update, you apply viscosity, apply the Goodenough. It softens, it smears the discontinuities, and things start to look a little more physical. That's more like it. This looks like if you look very closely, this is still something that is very weird. That looks bad. It oscillates. So imagine you're moving from a high pressure area to a low pressure area. Suddenly there's a potential. Suddenly the density goes up. That might look weird, but what is more weird is fluxes appearing out of nowhere. So you need to. This is a problem known as numerical oscillation. It's one of the biggest. Right now we are trying to deal with how to fix numerical oscillations in cleverer and cleverer ways. With windfall design, this problem shows up at cases of high frequency where wind is moving really fast to something that is highly optimized. So you get oscillations like this. The way we fix it is by ENO. ENO is essentially non-oscillatory, and we know ways that it's complicated. We do not bother with all that. There's a simpler way to do that. Goodenough showed that first order schemes are not oscillatory, second order schemes are. So suppose you have a switch that goes up every time you're encountering a very high discontinuous place, and then you switch on the first order, and then you move to a smoother place, and then you switch on the kth order. So then you get something like a hybrid scheme that interval is only between the kth order scheme and the first order scheme. So this gives you the hybrid scheme. This is the switch. So this is the case where the discontinuity is high, and this is the case where the discontinuity is high, and the switch is turned off. It goes to 1, and the first order scheme gets activated. So this is beginning to look a lot like it. But what is the point of this? If you can solve for 1D interference, you can solve for arbitrarily long 1D discretized distribution. And it might look that the Riemann problem is very unphysical in nature. Obviously, you cannot have suddenly move from one state space to one something entirely different in real life. But that is what happens when you go pixel by pixel basis. You have some amount, and there is a very sharp decline when you are going to the next pixel. So if you can simulate this, you can solve for an arbitrary 1D. You can solve for 1D, you can solve for 2D. And one interesting thing that happens if you solve for 2D is words open for you. You can do very beautiful simulation. This solver is not mine. This solver is just a Gauss single. It's solving just very simple linear fluxes. Solver is not mine. I will show the implementation because if you do it during Google, my computer is not good enough to handle it. Yeah, so this is showing this phenomenon called vortex shedding. This green triangle here, and you have these oscillations. Fine. So you correct for we are working with piecewise linear schemes. Here is the bulk of my paper. My work was done. And suppose we had instead of just keeping the this quantity here, we kept the slope as well. So instead of moving from piecewise constant, we move from piecewise approximation. Then how would these schemes look like? It will look like something known as MUCL approximations. We're going to start more devices centered differential scheme that use this MUCL methodology, and this is how they analyze derivatives. So as we saw that flux gets unphysical. So if you have a peak, this just gives you a derivative of 0, and this is not very important. Okay. So you start with this piecewise linear scheme. You calculate the spread. This is where information can propagate in linear time. You integrate over this chunk where information has propagated, and you forget about this. And then finally, you integrate over your original interfaces, and this is where your update rule comes. Ground load. This is the most beautiful graph I have made in my life. You cannot even see the approximate to the dots are my data points that the program spits up, and the red line is what we should have done. So with very small overhead, you get beautiful results. Modes of implementation. This is implements. So you might have seen how we are working by a for loop here. This is goes through the entire list by linear time. I realized that instead of doing that, computers are really fast with array manipulation. So instead of doing that, you shift the array, you just delete this element. So you have shifted xi to xi here, and you have xi plus 1. And then you just subtract this array from that, and then you get an delta x. So this is how we made it fast, and this is the hybrid switch implementation. Ghost cells are not necessary because in the literature, physicists do is add additional cells to the interfaces because the information might go there and then just repeat the cell. I realized you can just roll this entire index and keep running it. And I realized that instead of computing the flux derivatives analytically, component-wise is better and it works faster. It implements that shift function we just talked about right now. And this entire process of computing, 500 points takes 0.05 seconds. That's it. Thank you.
Where was the part of non-linear hyperbolic system?
This is one is in time, one is in space, so that's non-linear. Plus, you see that flux there. This flux that's used there, that is arbitrary. So no matter what flux you throw at it, it will just give you the same harmonious result. So that's when the non-linearity is coming.
Where is hyperbolic? Where is hyperbolic?
Hyperbolic is for, so you have a partial differential equation in second order partial differential equation. You have seen how a cubic equation looks like. So you know a cubic equation in x and y can be elliptic, can be parabolic, can be hyperbolic. Same way, you replace the polynomials with differential operators. Then you do that. So basically, a x squared plus b y xy plus c y squared and so on. So this is the cubic equation you know. Suppose you have a function that is derived, differentiate this twice, and so on, b x y u plus so on. This curve is hyperbolic if delta, which is I think it's 4a, 4b square minus 4ac is greater than 0, same thing. So that's hyperbolic. The Burgess equation is hyperbolic. This is the linearized Euler dynamics, is the Euler laws. Those are hyperbolic. A lot of equations in MHT is hyperbolic. They were trying to implement this in LHT. I know nothing about LHT. My work was in beginning. Please talk about it.
Can you explain the hybrid state again? Hybrid state.
Okay.
Not in detail. Just
Okay.
in that.
Yeah. So, we know a normal derivative in unit class. So implementing that is one step. You just go one step and you look at what the change is. That is first order scheme. First order schemes, good enough, sure, are not do not oscillate ever. But second order scheme always oscillate. So I want to get rid of oscillations. I want to show physical flux at places where intense phenomena is happening. So I will create a switch that looks ahead and future, and then I find that there is a good chance that that's a discontinuity. I will turn that parameter up to 1. If I am going through a smooth space, I will turn the parameter to 0. If I have this order switch, I can interpolate between the first order scheme and the higher order scheme. So I get good enough approximation here. Discontinuity is a really good approximation during smooth cases. And usually you get smooth curves. Like if it's a long enough line, it's a smooth line. But you get less errors because if there is a discontinuity, it knows how to do it.
Oscillation is in general a property of every single order.
Yeah, it is. But that's wrong because the flux is unphysical. Because it gets flux out of nowhere, and oscillation is there. I want to get rid of that because that's not how physical phenomena looks.
I'm trying to get,
Yeah.
I'm trying to think, like, why people at all look at, that's a property that we know.
Yeah.
There's always going to be,
Isn't it? I'll just turn the parameter down and just use first order.
so how are you actually checking what decided to the switching in your case?
So I have a parameter.
Where is something like this?
Yes. This is I'm throwing a lot at this one. So this is a theta. So near discontinuity, this goes to 1, and I'm using first order. And 1 minus 1 is 0, so I'm not using the theta. But near smooth cases, this goes to 0, that goes to 1. So suddenly I'm using the higher orders. You're asking how the switch works.
Thank you, Bhaushan, for the presentation. Now, heading towards the last presentation of the day, I invite Mansi Fish from Ashoka University. Please come and present.
But that does not require that. But I could understand I saw here, I could take care. And you ask for the details.
Hello everyone, I'm Ansiba, I'm from Ashoka University. I'm going to talk about my work on studying the H1 emission using our low-cost horn antenna that was made in Ashoka University. So we start by explaining what H1 emission is. H1 emission is emitted by neutral hydrogen atoms. Neutral hydrogen is just one atom of hydrogen, no ionization molecule. It occurs when there is a spin-flip transition. What a spin-flip transition is so you have your electron spin, you have your proton spin. When they're parallel to each other, this is a slightly higher energy configuration than when they're anti-parallel. So once, in a very rare chance, this electron spin can flip. And once this happens, this 1420.4 megahertz radiation is emitted. The wavelength of this radiation is 21 centimeter. That's why this emission is often called 21 centimeter emission. This happens very rarely, once in like 10 million years in one hydrogen atom. Which is why when we want to look at this, we look at really large sources of hydrogen, which are large neutral hydrogen clouds and our galaxy. This emission helped discover a lot of things and prove a lot of things. So it helped us visualize the spiral arms of our galaxy. It helped us find the rotation curve of the galaxy, and it also serves as a kind of a proof for dark matter. How I captured this H1 emission is using our horn antenna, which is this thing. It is made of this metal horn, which is a funnel-shaped thing, which has an aluminum coating. This horn is a waveguide for the radio waves that we want to capture. It sends the radio waves into antenna over here, and then from the antenna, the signal goes to two amplifiers, a bandpass filter, and finally RTL SDR. RTL SDR is just a dongle that you plug into your laptop, and it converts the electrical signals from these electronics to a digital signal. So you can analyze your thing on your laptop. To motivate my work, I will start by explaining the previous method of analysis that was used. To do this analysis, you take a ground reading, a sky reading, and a source reading. Ground reading is just pointing your antenna to any place which is not a radio source and which is not reflecting. So say a patch of grass or just a wall. Sky reading is any part of the sky that does not have the galactic arm or any other major radio source. So like not the sun, not the galactic arms, not any planets, any other part of the sky. And the source is the part of the sky that we want to take attention from. So the galactic arms, the arms of the galaxy, are this one. And we can notice here that this part over here at 41.4 megahertz, we see a slight peak in the source emission. We also see that slightly in the sky emission. Purely because neutral hydrogen is so abundant that it's very difficult to get a patch of sky which does not have any H1 emission. So what we do after this is you had a power axis and a frequency axis. You convert these to a temperature axis and a velocity axis. And using these formulas, you get this left graph over here. But what we see is we are left with a skewed baseline. This baseline represents any other signal than the H1 emission. So anything that is coming from, say, a receiver, any other noise in your system is reflected by this, not reflected, as in this slight slope shows that noise. So what we were doing previously was we were just estimating a polynomial to this and subtracting that from our signal to get, say, a flat baseline, and this was our final H1. We did not want this because this baseline was just estimated as like one polynomial. We wanted to actually take the ground signal, which is non-radio signal, to get a baseline and then subtract it from our H1 emission. So we're actually subtracting a radio baseline to do all that was how I got this project. So the objectives of my work were first to figure out a relation between the power and the receiver temperature. Receiver temperature is just the temperature of the electronics in the horn antenna. So if we assume that you turn on the horn antenna and the temperature of the receiver slowly increases with time and then it stabilizes at some point, you will also see that the power will also increase like that. And if we take our readings during that time when it's increasing with time, you will not get exact values. So you would want to minimize the receiver temperature contributions, right? So we can just subtract them at the end finally. So we wanted to do these, and then we wanted to find a real baseline using the frequency search method, and then we wanted to also use the frequency search method to analyze the HV signal. And finally, with the results of all of these, I also plotted the galactic coefficient group. Starting with the first objective, find a relation between the power and the receiver temperature. I pointed the horn antenna to, say, a patch of grass and let it run for some time. And this is power as a function of the time. So we can see that it increases for some time, and then after, say, like 30 minutes, it comes to a stable point somewhere. And we wanted to essentially study how, like, say, this grows with temperature or time, or what can we do to minimize these effects. So what we did was we installed a thermal sensor in our electronics with either the amplifiers with, say, thermal peaks and everything over them. And then what we saw was that right after putting this thermal sensor, we had our power with respect to time. It increased for some time and then stabilized instantly, which essentially solved the problem we were looking to solve. Because I think because of the thermal freeze we used, it helped our system, our electronics conduct the heat better. So the power just stabilized pretty quickly. So now we could just wait for 10 minutes after switching on the horn antenna and take our observations without learning. Then the next thing I wanted to do was work with frequency switching to analyze the H1 signal and get the baseline. So frequency switching basically is you choose a center for your observations and you choose a bandwidth. So for us, the center we chose was 49.5 MHz as it's close to the frequency that we want to observe, and a bandwidth of 2 MHz. So the curve that you can see here, the blue and the orange curve, they're at the center. And once I've gotten this data, what I do is I shift the center by 45 MHz to the left. So this green graph over there shows this frequency shifted. And then I bring it back to the center again, taking this orange curve, and then it move it right by 0.5 MHz again, taking this red range. And we can see here that the Asian emission lies at 14.4 MHz per object. And I did the same thing for our ground wavelength also, frequency expression, and I converted the frequency axis to a delta nu axis by this this is our delta nu. And so this, what this does is, this mu naught over here is the shifted center that we have chosen. So for the center ones, it will be 14.5 over t. But for the left shifted one, it will be 14.20. For the right shifted one, it will be 14.21. So what it does is, it brings all these curves together. And now, using the ground one, I want to get a baseline on my data. So what I do is, I add the two centers up, add the two left shifted ones, and then I subtract the left and right from the ground, which gives me a flattish baseline. I do the same for my source data also, and that gives me these 3 peaks. The negative peaks I get because I subtracted the left and I subtracted the right, but I added the two centers. So what I could do now is just take this much of the data and ignore the rest, subtract the baseline, and that would be my final H1 profile. But we decided to also use this signal. So we chose the points where the signal was intersecting the baseline. Flip the single paragraph to an average with this. So we use frequency switching to say like get an average of the four H1 emissions that we are taking. So it gives you basically a better segment over noise ratio. And finally we have our H1T and our baseline. And what we need to do is just subtract the baseline from the H1T. And once you do this, you have velocity. Velocity you do just by multiplying this with C. And that we can recognize as just the formula for a dot. And you convert this axis to a velocity, you convert this axis now to a temperature. Why we want to convert this to a temperature is because we want to see the brightness temperature of the hydrogen fuels. And we do that by using the ground and the sky data. So you know that the ground data is at some constant temperature, say 300 Kelvin, and the sky is also at some constant temperature. So this is sky which is at 5 Kelvin. And so you assign this entire curve 5 Kelvin, this entire curve is 300 Kelvin. And using these curves, you figure out the ratios. So say like temperature by power. And when you multiply that ratios to the power over here, you convert this axis to a temperature axis. So that is what we do finally. And these are my final results for some different galactic orbitals and atoms, basically different points in the galactic ones. And we see the H1 emission and orbital. And finally, what I did with these results is I found the maximum velocity for each of these graphs. And what I assumed was that at all points when I'm looking at the galaxy, I'm at least intersecting one of their say orbits. So this is me. There is a hydrogen cloud over here which is moving in the same direction as my line of sight. So the maximum velocity that I'll see in my graphs will be the velocity of this thing, because we can only see the radial velocity. And plotting those velocities for different distance to the center, we get this rotation curve, which increases for a bit and then stabilizes, which is what we expect when we have theorized down. So that was basically it.
Have you ever isolated H1 with spectrum method?
So
In
we
a
can't.
bottle. In a bottle.
In what?
In a bottle. Or any experiment.
No, it's so rare that like basically you cannot do it. Yeah, that's why we look at these galactic sources, which are like big hydrogen sources. To get
So this is a spontaneous transition, or there are any kind of factors going this one?
This is spontaneous, but over like the lifetime of the stage is basically very very long. So it's spontaneous, but like over a very long, very long.
And yesterday, when I did it, how do you get to more?
How did I get those?
I mean, in this, use the lower points, it is not working.
So these.
I could not observe. So, these are lower, closer to the.
Yeah. So the closer I go to the center of the galaxy,
So
this doesn't really make sense because I can't really take the maximum velocity over there. Because I know the closer I am to the center, the closer like the velocity should be to zero. So these closer values are not as reliable as like these higher.
So this is very, that's what I was very leaning on. So because it was a indication. Okay. Now one more thing, did you use velocity vector method to find the uniform velocity? There are two methods to give further.
Yeah, so basically I used these types of people.
So you use the velocity vector.
Yeah, we know outside.
Yeah. So the oops constants.
Yeah.
Use the oops formulas. Did you try doing a tangent formula?
So
Which you did for certain
objective of my work was to find the HVAC because we were working mostly on developing a lot of payment systems. And this is just what I did at the end of it.
So the method that you are saying, frequency switching.
Yeah.
You write down your whole, I mean, how do you implement it? I'm very curious.
As in, did I write like my own algorithm?
Yes, did you write your own algorithm?
Yeah. So it was basically under Professor Debankar. So I was getting all directions from him, but I wrote the entire algorithm.
You go to one more thing that I'm curious about is the sensor that you put. What was that sensor? Do you have the specifications?
Just like the PD100.
So you share the details.
I'm not sure what exactly it is. Like,
I can do it.
yeah.
Well, that's interesting because I was stabilizing, to stabilize the whole thing to take the data usually takes a long time.
Yeah.
So you took data, so one data point that you have here, each of these data points that you have here is one day observation, single observation. Or is it like, so when you say this one data,
Yeah.
so it's like just one observation, single observation.
Yeah. So
On a particular day.
on a particular day, but all of these are on the same day.
That I understand. They are the same way, you are tracking the galactic center, but these are all single day,
Yeah.
not means of performed over days.
So because the final objective was to get these profiles, I didn't have
What a beautiful
that.
profile.
Yeah.
It's very clean.
Yeah. So I tried it many times, got many offerings, but like it was just outside the research projects. I just wanted to do it on my own, so I tried to do it with the profiles that I had. So I couldn't really do like taking needs over multiple days. So it was just one day coming. Like one day when I got good data.
So how are you calculating this radial distance? Were you aware about the RO in depth of load, etc.?
So when I take my observations, I note down the all tasks of what I'm taking and like day and time of the meeting, and from there I calculate our data.
Also, have you put something for alignment? How are you actually, so when you are moving your arm, how are you measuring the, what are you using to measure the?
It's actually pretty rough, like the directions. So we just.
So I have seen your mount.
Yeah. So what I was using, which won't be like completely correct, is just my phone to calculate the
also.
Yeah. So because like the compass won't go perfectly because of the it's not completely reliable, but it gets like the rough direction.
Just there and say you can always find out that day,
Yeah.
at that moment of time, what the architect of that. You keep tracking it. Have you observed anything else in your underlying?
Not really. So we made the format data for this experiment, right? So which is why all the amplifiers and the other electronics that we have are all centered at like 1400 megahertz and 1400 megahertz. They're just for this experiment. So if there are any other like observations that we can do in these ranges, then we might use it for that. But for now, we're using it for HVAC.
Thank you, Mansi, for the presentation. Now, to end the day, I would like to invite Devanshi for the vote of thanks. Thank you everyone for staying so late. I understand we're running a bit behind the schedule. We'll try to correct it tomorrow. I'd also like to invite the participants of today to attend tomorrow's presentations. And to end, I'd like to thank the judges for their time and their patience. Thank you so much. See you all tomorrow.